Hello, our first keynote speaker for ICSA 2020 is Professor Hyung-Sik Kim from Sungkyunkwan University. He is an associate professor at the Department of Information Engineering. The title of his talk is Towards Usable and Secure Graphical Passwords for Smartphones. Professor Kim received a Bachelor of Science degree from the Department of Information Engineering at Sungkyunkwan University, an master's degree from the Department of Computer Science at KAIST, and a PhD from the Computer Laboratory at the University of Cambridge in 1999, 2001, and 2012, respectively. After completing his PhD, he worked as a postdoctoral fellow in the Department of Electrical and Computer Engineering at the University of British Columbia. He previously worked for Samsung Electronics as a senior engineer from 2004 to 2008. Let's welcome Professor Kim with a big round of virtual applause. Professor Kim?
Definitely, we have several research challenges that need to be addressed for developing usable graphical password for small devices with a touchscreen. Please enjoy my talk. Okay, as you know, passwords are popularly used in most computing devices or applications. Therefore, there exist many previous studies to analyze security and usability issues for traditional text password. However, text passwords are difficult to use in mobile devices specifically. There is no keyboard, its touchscreen is too small to type complicated characters. For some users, it would be a time-consuming task to type more than 10 characters containing capital letters, special symbols, and numbers. Therefore, smartphone companies are trying to develop more user-friendly authentication methods for smartphones. The most commercially successful such example scheme is to use biometric authentication, such as fingerprint and face recognition. However, interestingly, password and PIN are still needed even when biometric authentication schemes are used. This is because biometric authentication schemes cannot sometimes work well depending on environment, while password or PIN can always be used in the same manner regardless of environmental factors. When a user fails a certain number of unlock attempts with a biometric authentication scheme or a device is rebooted, PIN or password should be used. Consequently, in this case, regardless of how secure biometric authentication factors are, the overall security of a smartphone is still determined by the strength of the password or PIN used. Suppose that we have multiple choices, multiple options, but in this case, this is just or condition. So if one of those authentication scheme, our authentication scheme could be vulnerable. Therefore, many graphical password schemes have also been introduced in both academia and industry to address the security and usability problem of traditional text password. Among those schemes, a graphical password called Android pattern is one of the most popular used authentication scheme, like this. However, like any user-chosen password scheme, Android patterns can also be vulnerable to various attacks. There exist several attacks to crack Android patterns, such as smudge attacks, sensor-based side channel attacks, shoulder surfing attacks, and gashing attack. Especially in terms of gashing attacks, the attacker's gashing capability is generally limited with a small number of failed attempts for mobile devices because we assume that the password hash cannot be revealed. That is, we typically consider online gashing attack model only with a limited number of gashing attempts. For example, in Android, if we fail to draw the correct pattern 20 times continuously, Android system shows the error message, too many pattern attempts, and the device is permanently locked. A previous study in ACM-CCS showed that the actual password space of user-chosen patterns is much smaller than the theoretical space of possible patterns. Surprisingly, unlike our expectation, the guessing entropy of user-chosen pattern is lower than that of random 4-digit pins. In our 2015 Kai paper, we also collected real-world pattern data and analyzed the security of user-chosen patterns. At the time, we found that the pattern distribution is highly skewed toward a small number of commonly used passwords. This slide shows 10 most popularly used passwords. Those lists are constructed by using our Ngram Markov model. We believe that those patterns are most popularly used. Probably you can see those patterns look simple and easy to draw. We can observe some interesting properties of those patterns. First, the lengths of all of those patterns are just 3 or 4. They are very short. Also, our patterns have just one single turn except for the 7th pattern. So their structure are very simple. All of those patterns start from left and move to right, and from the top and move to the bottom. We believe that those characteristics are strongly related to the direction of users' written languages. Therefore, if we know a user's written language, we can more easily guess the user's pattern. User-chosen patterns are totally different from random patterns. Graphical passwords are also vulnerable to several attacks, such as smudge attacks or shoulder surfing attacks. For example, when a user draws a pattern on a touch screen, there remains some oil residues on the screen as a side effect, like this. When you draw a pattern, we can see that there remains some oily residues on the screen, like this. Therefore, attackers can misuse this kind of side channel information to guess a victim's pattern. We call this smudge attack. Actually, we developed a fully automated pattern guessing attack by combining Markov model-based guessing attack with computer vision-based smudge attack. Our results were published in Asia CCS 2017. In the paper, we showed that our automated pattern guessing attack is very successful. We can successfully recover a secret pattern with 74.17% success rate. Even for the case after using apps such as Facebook intensively, we can still recover a secret pattern with about 32% success rate. As you know, in most security applications, there is an arms race between attack and defense mechanism. So against existing attack on the graphical password, there are also several defense mechanisms which were proposed. In Android patterns, there were many previous attempts to improve the security of user-chosen patterns. One approach was to change a grid layout. Some researchers found that the current 3 by 3 layout may lead to biases in choosing patterns. Therefore, they suggested to use a circle or random grid layout to avoid such biases. And also, a bigger grid layout such as 4 by 4 was also suggested to increase the theoretical password space of patterns. However, according to the previous experimental result, user-chosen patterns were still easily guessed, even, even when a bigger grid layout is used. It means that user-chosen patterns were still guessable. Another approach is to use your password strength meter, like traditional text password. The password strength meter is a commonly used practice to encourage users to choose passwords that are not easy to guess. We developed an effective password strength meter for Android patterns and evaluated its usability and security results. Based on our user study result, the guessing entropy can become higher when you use the meter. However, we found that the security improvement is still limited. For example, the starting point of patterns are strongly biased at this point, even when you use your password strength meter. For example, a left and upper point was the most frequently used compared with other point. Unfortunately, the use of password meter cannot prevent users to choose patterns having such biases. Okay, how can we avoid this kind of bias? We believe that the use of password selection policies is a possible option to address this limitation. Password selection policies can be used to avoid weak password. Therefore, our work was motivated by the following research question. Can it design effective security policies for Android patterns to improve their security without significantly compromising their usability? To answer this research question, we designed CISPAR, a novel graphical password selection method, and evaluated its usability and security. To develop a practically working solution, we specifically consider the following 4 design principles. First, we tried to minimize additional memorability burden on users. Second, we tried to keep the authentication time similar to the original Android pattern logs. Third, we want to make users easy to learn and use. Fourth, we want to avoid significant software or hardware changes. Actually, Backward compatibility is one of important issue to use password scheme. With this design principle, we proposed CISPAR that is a novel system guided pattern lock scheme. Our idea is very simple. When a user creates a pattern, that pattern must contain small number of randomly selected points or lines. We already observed that pure user-chosen graphical passwords are vulnerable to guessing attack. Therefore, we need to mandate some random points or lines to increase the randomness of user-chosen patterns. For example, given the randomly selected point at the center, like this, the user should choose create a pattern containing the center point, like this pattern. To answer our research question, we defined three hypotheses. First, the security of CISPAR pattern strengths with the increase in the number of mandate points. This is our first hypothesis. Second, the memorability of CISPAR pattern decreases with the increase in the number of mandate points. Third, a CISPAR policy that shows no statistically significant difference in memorability against the original Android pattern has better security. Our user study and experiments were designed to validate those hypotheses. Okay, in our evaluation, we used the following 5 policies for user studies. The leftmost one is to use the original Android pattern lock. The last one is the random policy. In this policy, a system-generated random pattern is just used instead of using user-chosen pattern. We believe that original is the base case and the random pattern is the most secure one, but probably it produced some poor usability result. And also in the middle, those 3 policies are CISPAR policies used in our user study. Each policy defines the number of randomly selected mandated point that must be used once upon selecting a pattern. Those are CISPAR policies. To evaluate both security and usability of those 5 policies, we conducted a large-scale user study with 1,717 participants through Amazon's Mechanical Turk. For this user study, we developed a screen lock application for Android. We then conducted a between user study between 5 different groups independently. Therefore, the participants were asked to select a pattern under one of the 5 policies independently. We collected the data to examine how users choose a pattern and use it to unlock their device. After finalizing the pattern setup process, we asked the participants to complete 2 remembrance training tasks to help them memorize their pattern. And then they complete a lexical puzzle to wipe out their short-term memory. We followed up this user study method from previous password research study. We have 3 record tests for memorability evaluation after 5 minutes, 15 minutes, and 24 hours, respectively. In each recall test, if a participant correctly draw his/her pattern within 5 chances, we regard that the participant passed the recall test. From the 3 recall tests, we measured the recall success rate. We counted the number of remaining participants who successfully recalled their pattern against the number of initial participants. As you can see, this table with all CISPAR policies, we obtained similar recall success rate to the original policy. Interestingly, in the second and third tests, the participants under the 2-point CISPAR policy successfully recalled their pattern better than the participant under the original Android policy. We also measured the authentication time of each policy. We can see that the participant with randomly generated pattern took a long time, as we already expected. However, there is no statistically significant difference between the original policy and our other CISPAR policies. This is a very good signal. We also analyzed the number of attempts of each policy. Random participants drew their pattern twice on average, indicating that the use of random pattern incur a significant usability penalty. Again, we cannot find any significant difference between original and or other CISPAR policies in the number of attempts. We analyzed the guessability of the collected pattern to evaluate the security of policies. Even though we collected a large data set consisting of 1,717 patterns, it is not sufficiently large to calculate the guessability of all possible patterns. Therefore, we estimated the probability of all possible pattern occurrences using a probabilistic password model such as N-gram Markov model. How can we estimate the probability of a given pattern 1, 2, 3, 6, and 9? We can see that a pattern is consists of consecutive points in a sequence manner. That is, we believe that a pattern can be regarded as a sequence of consecutive events. Therefore, an N-gram Markov model would be a suitable probabilistic password model to approximately estimate the probability of each pattern. The probability of a pattern consisting of x1, x2, xm can be calculated as the probability of x1, x2, xm minus 1 multiply the product from I equal n to m, the probability p xi bar xi minus m plus 1 xi minus 1. With the collected pattern, we constructed a 3-gram Markov model to estimate the probability of all possible patterns. So, for example, a given pattern 1, 2, 3, 6, and 9, we can calculate its estimated probability like this. P2 bar starting symbol 1 multiply P3 bar 1, 2, and so on, like this. So if we compute each probability for each 3-gram string, we can calculate the probability of a given pattern 1, 2, 3, 6, 9, like this. So in our data set, disparity is approximately the same as 0.039 and so on. Okay, from the constructed 3-gram Markov model, we estimate the distribution of all possible patterns. We then compute the partial guessing entropy for the distribution of all possible patterns. The partial guessing entropy is a standard metric which is commonly used to evaluate the security of password schemes. Our study results showed that the patterns generated with the CISPAR policies have a significantly higher guessing entropy estimate than the original Android patterns. Guessing entropy result can be interpreted as follows. 20% of the original Android pattern can be successfully guessed within only 10 guessing attempts. However, if we apply 1-point CISPAR policy, the number of guessing attempts should increase up to 53 guessing attempts to crack 20% of the patterns. And also, the 3-point policy, but in this graph, interestingly, we can see that the 3-point policy was not good as much as other CISPAR policies. From this graph, we can see that 1 point has the highest guessing attempts. In practice, we developed a dictionary of the top 20 frequently used patterns based on the 3-gram Markov model we constructed. Our cracking result showed that about 32% of the original Android pattern was successfully cracked within 20 guessing attempts. However, all CISPAR policies were cracked less than the original Android patterns. We can only successfully crack for 2-point pattern with 9.36 attack success rate. Unlike our expectation, 3-point policy was not effective as much as other CISPAR policies. To evaluate the security of the policies, we also analyzed several statistical characteristics of a pattern under each policy. We first analyzed the frequency of the starting point because the starting point of the original Android pattern are quite skewed. In our experiment, we can see that a majority of original pattern was still started with upper leftmost point. However, in CISPAR policies, this trend seems clearly weakened, although the upper leftmost point is still more frequently used compared with other remaining points. We also analyzed the frequency of the ending point. Interestingly, the ending point is also biased. Participants prefer to use the bottom rightmost point as an ending point of their pattern. However, we failed to find a significant difference between all CISPAR policies and the original policy based on our statistical test, Fisher's exact test. We also analyzed the frequencies of the segments used. We define a segment as a line that connects 2 points together. In those figures, dark color means a higher number of segments was used. We can see that 1-point policy seems more evenly distributed than the original policy. We also analyzed how given mandate points are used in participant pattern. We observed that a majority of CISPAR participants prefer to use your mandate point as the starting point of their pattern. Interestingly, for 2-point and 3-point policies, a mandate point is also frequently used as the fourth position of their pattern. We believe that one of the mandate point could be used frequently as an ending point. Okay, it's the time to revisit our hypothesis as I already explained at the beginning of our presentation. The first hypothesis is that the security of CISPAR pattern strengthens with the increase in the number of mandate points. However, we cannot accept this hypothesis because the use of 3 mandate points is not helpful to improve the security of pattern. So we just reject this hypothesis. The second hypothesis is that the memorability of CISPAR pattern decreases with the increase in the number of mandate points. We found that the memorability effect of increasing the number of mandate points is unclear. We failed to find a significant statistical difference between CISPAR policies, so we cannot accept the second hypothesis too. The third hypothesis is that a CISPAR policy showing no statistically significant difference in memorability against the original Android pattern has better security than the original patterns. In terms of memorability, none of the CISPAR policies showed statistically significant difference against the original Android pattern. In terms of security, all CISPAR policies outperformed the original Android pattern. Therefore, we believe that CISPAR policies can potentially replace current Android pattern without compromising too much usability, including memorability. Okay, until now, I just explained the security and usability of Android pattern. So probably if we use a CISPAR policy, we can improve the security of Android pattern without compromising memorability. And also, as a further work to improve the security of Android pattern, we can consider designing a free-form gesture password. This idea and evaluation result was presented in Auckland this year. Okay, as you can see, we can create a free-form gesture password rather than grid-based Android pattern. Probably the free-form gesture password can be a secure and usable option for touchscreen devices because theoretically it has much password space compared with grid-based password scheme. However, we have several challenges in using gesture password. Every time gestures can be drawn differently, unlike Android pattern on a grid layout. Therefore, we need to use your similarity measure-based recognition. Moreover, there is no standard method for constructing common security metrics such as guessing entropy for gesture password, making it hard to contrast gestures against other authentication methods. For example, existing studies just use the calculation of equal error rate or manual unlock success rate. Probably those metrics are not sufficient to evaluate its security. Therefore, we deployed our gesture password application on Amazon's Mechanical Turk again. We recruited 2,594 participants in total. We collected more than 13,000 gestures. This data set is the largest gesture password data set, which is between 5 and 25 times larger than prior gesture password data set. In theory, as I already explained, the gesture password space is not finite. Therefore, to compute the guessing entropy of gesture password, we need to discretize their password space. That is, given a gesture password, we extract its substrokes and then map them into symbols representing the length and angle of the gesture password. This figure shows some discretization process. We constructed 570 different Ngram Markov models to find a suitable Ngram Markov model. We optimized angle and length categories. The optimal model has 10 angles, 3 lengths, and large overlapped boundary. Actually, we also need to consider overlapped boundary for freeform gesture. This figure shows the distribution of initial strokes, center strokes, and final strokes. We can see that the distribution of initial strokes is relatively biased compared with the distribution of center and final strokes. We developed a novel attack method using gesture clustering result. We first compute similarity scores between all gestures. Then we cluster those gestures into several different groups based on the computed similarity scores. Next, we found the top 20 largest cluster. And then we create the gesture password dictionary by selecting the representative one from each of the top 20 largest cluster. Then we can perform the dictionary attack with this gesture password dictionary. This figure shows the clustering result of gesture password. We can construct the dictionary of most common gesture password by selecting the geometrically centered gesture from each cluster. So this is the dictionary of gesture password that we constructed. We can crack about 23% of, we can crack 22% of gesture password within 20 guesses. In theory, the password space of gesture password is very huge. However, we found that user-chosen preform gesture passwords are still vulnerable to guessing attack in practice. To overcome this limitation, we consider two gesture password policies: lexical policy and blacklist policy. For the lexical policy, a random word is given. We expect that the given random word is used to inspire users select more diverse gesture password. And for the blacklist policy, a list of 20 common gesture password is used as a blacklist. That is, users cannot select their gesture password that are similar to those common gestures in the blacklist. We expect that the use of a blacklist is helpful avoiding common gesture password. Here is our final cracking result under those policies. Unfortunately, we obtained 34% cracking rate under the lexical policy, unlike our expectation. Actually, lexical policy is not helpful to improve the security of freeform gesture password. However, we obtained 17 cracking rate under the blacklist policy. So if we combine both policies at the same time, the cracking rate can be reduced to 15%. So we conclude that our blacklist and consolidated policies improve the security of gesture password while our lexical policy reduces it. A possible explanation is that the lexical policy does not require compliance, while it is mandated in other two policies, blacklist policy and lexical and blacklist consolidated policies. It ensures that participants cannot use one of the common uh, gesture password. Okay, here are my conclusion in this talk. User-chosen graphical password can be vulnerable to password guessing attack. However, we believe that addition of random lists can be helpful to improve the security of graphical password scheme without compromising the usability of those schemes if we use a smart password selection policies. Also, compliance might be better than recommendation to prevent poor security practices. However, as you know, we should carefully select compliance rules to minimize their effect on usability. Thank you. Do you have any question?
Thank you, Dr. Kim. I'm showing my appreciation by displaying hand claps there. Thank you so much.
Thank you.
Virtual clapping. And yeah, thank you so much for your very thorough presentation this morning. And I mean, we all developed definitely a better understanding of graphical passwords, especially on those mobile devices. And I mean, we also collaborated. I mean, Bill on this call and I also collaborated on another paper with you regarding this matter. So um, I was just going to ask you about the future of this research. So, do you feel that you've done enough in this area and
Yeah, I think
time to
that,
move on to something else, or what do you think? Just curious.
oh yeah, this is very important question.
Uh-huh.
Actually, I think that graphical password is very popular used in mobile devices, and
Mm-hmm.
also this scheme would be used in future in IoT devices with a touch
Uh,
screen.
yeah,
So I think that graphical password itself would
yeah,
be very important issue.
I see.
So it is very important to develop secure and usable graphical password
I
for
see.
IoT devices and mobile devices.
I
This
see.
is one of research direction
Mm-hmm.
still.
Mm-hmm.
And also, I think that maybe we can also consider the other option.
Mm-hmm.
At this time, we can also collect some users' behavior
Mm-hmm.
using their devices and application.
I see.
So with this information,
Mm-hmm.
maybe we can identify a specific user. So we call this behavior fingerprint.
Mm-hmm.
So maybe app usage information and user's location information could be used as an evidence of user itself.
Mm-hmm.
So I think that this is another research direction to design usable and secure authentication with some user's behavior information.
Mhm. Yeah, thank you so much for your answer. And I was also thinking about this adoption
Mhm,
of graphical user passwords because
mhm,
I mean, if they use another form of authentication instead of graphical passwords,
mhm.
I was just thinking,
What kind of
like for example,
form?
we're still using passcodes and just traditional conventional
Mhm,
passwords, right?
mhm.
So I was just wondering, like, what fraction of the population is still using graphical passwords versus the traditional means of authentication and also other means. For example, we use now
Mhm.
uh, cameras to get authenticated too, right? So
Yeah. Face. You
yeah,
mean face authentication, right?
right. Yeah.
Yeah. So actually, as I already explained, bio bio based
Mhm.
authentication is very
Fingerprinting,
popularly used,
yeah,
yeah,
too.
such as fingerprint,
Mm-hmm.
iris recognition, and face recognition.
Mm-hmm.
But still,
Mm-hmm.
those information cannot be permanently stored in the device.
All right.
So maybe if we reboot the system,
Mm-hmm.
secret-based
Mm-hmm.
password is necessary.
I see.
So PIN password is permanently used,
Mm-hmm.
and also maybe if we believe that biometric authentication is
Mm-hmm.
very secure,
Mm-hmm.
but if the other option
Mm-hmm.
can be cracked, maybe the overall security of authentication
Mm-hmm.
would be reduced to the weakest link of
Nice.
authentication scheme.
Mm-hmm.
So if we can break one of multiple options, we
Mm-hmm.
can break the authentication of
I see.
the system. So I think that regardless of the percentage
Right.
of usage,
I see.
password, PIN, graphical password
Mm-hmm.
would be very important issue.
I see. So it still plays an important role in overall authentication in general.
Mhm.
That's what you're saying. Yeah.
Yeah,
Yeah. Got it. Yeah.
because biometric authentication has some limitation.
I see. I see. Yeah. Definitely. Okay, so I'm going to open this opportunity to everybody participating. Do you have any questions for Dr. Kim, our keynote speaker? I'll give you.
I would have a short question.
Oh,
Okay.
Dr.
Hi,
Cho, I have
Simon.
a question. Hello.
Yes, hi. Uh, when it comes to the policies, did you also consider uh, policies with like recommendation for a length or for like a number of loops or edges or something like that?
Yeah,
Would that be a way to make it more secure?
actually, in general, we can consider many different options, such as inclusion of edges and inclusion of point, and also exclusion of point and exclusion of line. But we just reduced a small number of policies only for Android pattern, because if we consider many different choices, we should recruit a lot of participants. So it is not possible to perform. So we just reduced a small number of options in designing policy. But and also we already did some pilot study with many different policies, and we found that some complicated for some complicated policies, users cannot understand them. So maybe it would be better to design very simple policy. But still, I think that we have some possibility in using more advanced password selection policy.
Okay, I understand. Yeah, of course, for the usability, it's 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 bad to make too much uh, policy.
Yeah, because actually our goal is to design a graphical password scheme which is very similar to existing original Android pattern. So if we use a complicated policy, probably user cannot understand, and also maybe learnability would be decreased. So we just use a simple policy. We found this observation from our pilot study.
Would it be possible to use the signature?
Yeah,
As a
actually, our
signature?
preform password gesture can also include some user's signature.
Mhm.
So it is possible.
Okay, thank you. And the one last question maybe from my side, the data set you acquired, is it available freely, or is it like closed for your research group?
Unfortunately, at this time, it is not possible to share our data set with some public institute because when we collect the data set, we did IRB, and also in the IRB, and also we noticed we did not share our data set with others. So it is not possible to share our data set.
Okay, thank you.
Okay.
Thank you, Dr. Kim. And we have time for probably one more question. And if you have any questions, let us know. Anybody? Any questions for Dr. Kim? Okay, 1,000.
I
Okay,
can
good.
ask a question.
Doctor, not doctor yet. Actually, just eventually.
You can just give me my PhD. I don't need to work for it.
No way. Okay, go.
Yeah. So, Dr. Kim, I'm curious what you think about like the really long term of pattern locks, or pattern based authentication is in smartphones, because I also agree. I understand all the scenarios where we need something that's not biometrics, it's not facial, it's not fingerprint, but all of the work that you do, I repeatedly see all of your work showing that many of these schemes are they just don't seem to hold up on a lot of robust attacks, from computer vision to neural networks and all sorts of attacks. What do you see in the long term with pattern-based authentication? Do you think they'll find a way for it to be really robust over the long term?
It would be a very difficult question because maybe in future, maybe we can develop a more advanced authentication scheme, replace existing graphical password. Because as you know, passwords just provide some marginal security. So definitely compare with some cryptography based authentication scheme, password scheme would not be comparable in terms of security. So probably I think that finally we can develop more advanced user authentication scheme using some hardware device or wearable device. In this case, probably we can replace existing graphical password with the other smart authentication scheme. I believe that password is just an intermediary solution, but still in web authentication, we can use text password. It has very long history, and also in mobile device, we can still use PIN and graphical password, even when they are very weak and they provide very marginal security.
I see. Okay, I agree. I certainly hope they come up with some more robust authentication key schemes at some point. So thank you. I appreciate that.
Yep. Definitely in future, we can develop a more advanced authentication scheme. This is just interim solution. Yep.
Okay, I think time's almost up, and thank you again, Dr. Kim, for your very insightful keynote speech this morning, and we all learned much more about graphical passwords and the authentication schemes. So thank you again for your contribution to our conference, and let's give Dr. Kim a big round of virtual applause by displaying your clapping icon.
Yeah,
I'm
thank
doing
you,
it.
thank you. Thanks a lot. Yep.
Yeah. Thank you so much.
Next year, yep, I will introduce more interesting talk.
Oh yeah, we're looking forward to it, and hopefully we can do an in-person, meeting next
Yeah,
year.
I hope so. I hope so.
Yeah. Thank you so much.